So next aspect undergoing the coordination compound is the structure and back bonding. Structure and back bonding in metal carbonyls. Structure and back bonding in metal carbonyls. So for instance, we'll take some of the metal carbonyls, students. For example, NiCO 4 times that we have seen this. We'll write the structure of these compounds, few of the metal carbonyls, which could be asked. How many bridging bonds are there? How many MCO bonds are there? These kinds of questions could be asked. Or the structure and the hybridization may also be asked. FeCO 5 times. CrCO 6 times. Right? So this is the mononuclear complexes. So these are mononuclear complexes. Mononuclear complexes means you have only one central atom. You have only one central atom. The structure will be regular. If there are, the 4 ligands, 4 carbonyl ligands, that is, it is tetrahedral and sp3 hybridization. If there are 5 carbonyl ligands, then it is trigonal bipyramidal, and the sp3 dehybridization, trigonal bipyramidal and sp3 dehybridization. And if it is the octahedral, it will be obviously the octahedral complex. The 6 ligands, if it is there, CrCO 6 times, it will be octahedral complex. And the hybridization is D2sp3, because hybridization is D2sp3 because of the fact that you have the carbonyl ligand, which is a very strong ligand. Here also it is dsp3, that is, you have trigonal bipyramidal structure. Inner d orbital will be involved in the hybridization. The structure is usual, nickel tetracarbonyl, tetrahedral in shape. Geometry is tetrahedral. This is the structure. FeCO 5 times is trigonal bipyramidal, right? Trigonal bipyramidal, CO and CO, and the CrCO 6 times is its octahedral complex. You have 6 ligands at the 6th corner of octahedron. So this is about the mononuclear complexes. Sometimes they may ask you about the structure of dinuclear complexes. We'll write the dinuclear complexes. Few common dinuclear complexes will take it and we'll write the structure. That is, the normal common one is CO2 CO 8 times and the Mn2 CO 10 times. Okay, so if you consider this, obviously you will come to know that there is a CO-CO bond will be there. In a molecule like this, you will be having CO-CO bond will be there because it's a dinuclear complex. So you have 2 metal ions, so metal-metal bond will be there. They may ask you how many CO-CO bonds are there, 1 CO-CO. And interestingly, 2 of the carbonyl atoms, carbonyl ligands are bridged ligands, and the rest of the 3 will be 3 in each case, because there are 8 ligands are there. So 3 will be terminal ligands for each cobalt and 1 will be bridged ligand. So, or in other words, total of 6, the total of 6 terminal CO we have and 2 bridging CO we have. I'll repeat, important students, just remember CO to CO 8 times could be asked. How many terminal COs are there? How many bridging COs? We have 6 CO terminal CO and 2 bridging CO in CO to CO 8. So as far as this is considered, there are no bridging carbonyl here, so M and Mn are connected. Right, then you have 5 carbonyl ligands will be there, which is directly connected in each case, CO. That is, each manganese will be having carbonyl ligand. So this is the structure of Mn2CO 10 times. Very clear. So this could be asked, just keep it in mind. The important aspect in this is the back bonding. Back bonding part has been asked a number of times regarding the back bonding. So the back bonding in carbonyl complex, that means if you see the spectrochemical series, you will observe one thing. See, although the CO is a neutral ligand, it is placed at the bottom of the spectrochemical series, or in other words, CO is a strongest ligand. CO is the strongest ligand. Why? Because there is a back bonding in the carbonyl compounds. Back bonding in carbonyl containing metal complex or the coordination complex. So carbonyl ligand in the coordination complex goes for the back bonding. What it means to say that lone pair of electron will be donated by the carbonyl group to the central metal ion. Alongside, what happens is metal ion gives back the electron to the carbonyl. What happens is MC bond turns out to be like a double bond character. Right? So in all the cases, rest of all cases, there will be a bond between the metal and the ligand. That is, a coordination bond happened between the ligand and the metal in rest of all cases. It's purely a single bond. But if at all the carbonyl group is there, carbonyl group will give the lone pair of electron from the carbon. From the carbon, the lone pair of electron will be transferred to the metal. And metal gives back the electron to the ligand, or in other words, the second bond also will be formed. That is, it is a back bonding happens. That is, metal gives back the electron to the carbonyl, or in other words, the metal carbonyl bond or the MC bond turns out to be having a double bond character. That is what makes MC bond to be stable, or that is what makes the metal carbonyl to be stable, or that is what makes carbonyl ligand to be of strong ligand. Why carbonyl ligand is a strong ligand? If someone asks you, the answer is it is because of the back bonding. How does the back bonding happens? That is, if I am having a C double bond O, that is C triple bond O, this is basically donated by the oxygen and having a positive charge and a partly a negative charge. I can write one, this is carbon, we have seen the hybridization and the structure of the the carbon monoxide. This is sp hybridized. One of the sp hybridized orbital is utilized for sigma bonding, rest are pi bonding, and one of the sp hybridized orbital contains lone pair of electron. Remember, these two bond has been formed by the unpaired electron donation by this valence electron of the carbon will be participated in making these two bond, and rest of the two valence electron will remain on the carbon. That two valence electron will be making a pair and positioned on the sp hybridized orbital, and there is a coordination bond. This bond is basically coming from oxygen to the electron transfer from oxygen to the carbon. You don't worry about that. Right? This unpaired electron, this lone pair of electron which is present on the carbonyl ligand will be donated to the central metal ion, and this is how the coordination complex, that is the metal carbonyl complex, will happen. That is, the the lone pair of electron on the carbon will be donated to the metal. And this is how we will be having a metal carbonyl bond, a coordination bond will be established. That is why we will be having a metal carbonyl complex. But interestingly, what's been observed is metal will be having high electron density because it has taken a lot of electron from the ligands now. Electron density of the metal will be keep on increasing. What metal does is, metal gives back the electron to the, the carbon atom. Metal gives back the electron to the carbon atom of the carbonyl ligand. Where it goes? It goes to the students, if you consider the molecular orbital theory, this is C triple bond O. That is, you have a carbon and oxygen, 8 plus 6. The number of electron is 14. That is sigma 1s2, sigma star 1s2. Sigma 2s2, sigma star 2s2. Sigma, the pi to px2, pi to py2. And sigma to px2. And the next orbital is pi star to px and pi star to py. This is empty. Rest of all orbitals, 14, it is filled, nitrogen-like structure. Rest of all orbitals are filled, and there is an antibonding orbital, pi star antibonding orbital, that is pi star to px and pi star to py antibonding orbital will be present on the carbon atom, which is basically unfilled, which is not filled. Pi star to px and pi star to py orbitals, or the antibonding orbitals of the carbon atom in the carbonyl ligand is unfilled, not filled. That is, it is empty. Since it is empty, it can take back the electron from the metal. When it takes back the electron from the metal, a double bond character will be established between metal and the carbonyl. That is, this bond is what we call it as back bonding, and which is responsible for the strengthening of the bond between the metal and the carbon, or this is responsible for the the strong ligating character of the carbonyl ligand in the coordination complex.